Hello. Welcome everyone. Happy New Year if you're just joining, and do feel free to say hi. I'll just give it a minute for people to log in and stuff, but welcome. Hopefully everyone can hear me. Yeah, so I hope everyone's had a good restful break as well from school and stuff, but do say hello if you're just joining. We're going to be looking at binomial distribution today, or binomial expansion, sorry, which filters into binomial distribution. It's on the pure and the statistics part of the A-level course. But yeah, we're going to look at it from the pure maths side. So that'll be really good. It'd be great to hear from people throughout. So if you want to say hi, share answers, share questions as we go, that would be great. Yeah, I'll give it a minute and then I'll share the screen. But I can see the chat, so if you want to say hello or ask any questions, do feel free to do that throughout. Let's have a little look. Excellent, and welcome to anyone who's just joined as well. Hi, welcome Zach, if you've just joined. I think I can see some messages coming through. How's it all going? Let me know as well, guys, what topics you're doing at school at the moment. Give me a little update. Binomial expansion might be something you did in the first term. It might be revision. For others, this might be very new. It's definitely quite a new idea at A-level. So whether you're in year 12 or 13, binomial expansion is quite a big idea. So it'd be great to get a little update for you. But welcome to everyone joining. It's great to see so many people joining so promptly. We're about to start in a second. I'm going to look at binomial expansion today. So yeah, welcome. I hope everyone's well. And it's not too stressful with exams and mocks and things, depending on what year you're in. But yeah, do say hello, do give me a little update on what topics you've recently been doing, and also if you've done binomial expansion before. Some of you might have done it and also met it within the stats part of the course. You might have done the binomial distribution as well. But I'm going to share the screen and I'll be taking questions and answers throughout. So do feel free to say hello at any point as well, and I can see your messages here, so that'd be great. But I'm going to get started. Thank you again to those that have joined so promptly. Hopefully you guys can see my screen there. So I'm sharing the slides and we'll work our way through some binomial expansion content. But as I said, oh, excellent. Thanks for the message there, Zach. I'm just having a little quick read. Welcome. Thanks, guys. Thanks for giving me an update as well, because obviously lots of people at lots of different stages on their kind of maths journey, and it's very full on at this point of the year. We've had the big term out of the way. That's great to hear, Zach, and it's good that you're like looking at the content ahead, which is brilliant. This is a really good topic actually to look at because it's quite new at A-level, so it should give you a bit of an insight. Roxana, that's great as well. So it looks like you've really cracked on with the pure content over the last term. So yeah, brilliant. Thanks for the updates then. Do feel free to anyone else that wants to sort of update us in the chat with what you've learned and if this is new to you. But this is a great topic to look at actually for the A-level because it's quite multifaceted. It comes up in lots of different places. So we're going to get started. Do feel free to ask me to go back or ask any questions. I'm Max. I do the maths teaching for Snap Revise. I'm the lead maths teacher. And I've been teaching A-level maths for sort of 6 years now, and GCSE and below as well. That's okay, Zach, no worries. So this should be last until 5 o'clock, but hopefully the stuff you see will give you an idea. And obviously the video will be uploaded afterwards if you want to watch the rest and see how you go with the content. So yeah, thanks for that, no problem. So what we're going to look at today, quite a nice new topic for a lot of people. We're going to look at this idea of Pascal's triangle, which filters into combinatorics, combinations, and all the binomial expansion stuff. We're going to understand what combinations are, especially this NCR button, which you might have seen on your calculator. I think on a lot of them, it's above the divide sign, and we're going to see what that does and what this is as an idea. And we're also going to learn to expand brackets, not just double brackets, but a kind of pattern and rule for multiple bracket expansions. So this is a really good topic to be looking at today. No problem. Excellent. So here we go. We're not going to look at the year 13 part of this, but it will give you a really good insight into how this topic will evolve and grow throughout the A-level course. So here we go. So to start with, if we just look at expansions of brackets that maybe we've done before, for example, the first one, you might have used a method at GCSE that a lot of people call FOIL, first, inner, outer, and last. And remember that -1 is attached. If you want to share answers in the chat, feel free. But just going through kind of stuff we should be happy with. Hopefully everyone's happy that you times all these 4 bits together and then you tidy it up where possible. So do feel free to share answers in the chat. But I'm going to work through these anyway. So hopefully we can see that that should tidy up as follows. So hopefully we're all good with that. Now, when it becomes a triple bracket, it suddenly becomes a bit more work. So it's handy if we've already expanded the first 2. You can expand them kind of in any order, really, but as long as you've multiplied everything by everything effectively. So it gets a little bit more tedious when we introduce a third bracket, which is why we actually look for a kind of shortcut technique. And that's what we're going to look at today. So there's quite a lot to times out and tidy up here. But just check you're happy with this. So the first term is going to be x cubed, and then we're going to get plus, let's have a little look. So x cubed plus, if we get 3x squared, and then we're going to get another x squared. So if we tidy this up, plus 4x squared plus x minus 6. But we'd have to do an expansion of lots of different things and then tidy them up. Likewise, what we're going to focus on is generating a little rule. So if we have like x plus 1 squared, hopefully everyone's happy that that's a double bracket of the same thing. And this is a triple bracket of the same thing. But by the time we get to x plus 1 to the 10, we definitely don't want to be doing 10 brackets of expansion. So we kind of need a little rule for this. This is too tedious. This takes way too long. So we're going to look at some patterns that emerge that you probably haven't explored before at GCSE. So this would expand to x squared plus 2x plus 1. This one would actually expand to x cubed plus 3x squared plus 3x plus 1 in descending powers of x. So just if you've just joined, welcome, but please let me know in the chat if you've ever seen the binomial expansion as a thing before, and we're going to look at that together today. So that's kind of prerequisite stuff. I'm hoping we're all happy expanding brackets and tidying them up. We're going to be looking at this factorial and combination stuff to get us started. Excellent. Okay, thank you. So some of you have done this before. Now this is a key part of the course. Whatever exam board you do your A-level with, whether it's Edexcel, OCR or AQA, this is a massive topic and it comes up, as I said, in year 12 and 13. So to start off with, Pascal's triangle, we're going to just talk about briefly. And Pascal's triangle is this nice kind of pattern of stuff that people get very sort of panicky about, like, am I going to have to write this all out? And you don't, but it is really handy to understand it. So basically, all rows start and end with a 1. Who has seen this before? And there's loads going on with this triangle. Like it does lots of other things as well. There's loads of patterns in there. It is really cool, but it kind of goes beyond the realms of the A-level to worry about all of that stuff. And then basically the next thing is the number of the row. So we kind of consider the top as like the 0 row. And then the number of the row. Sorry, I started writing 0 there. So basically, starts and ends with a 1. And this is actually quite useful, this triangle. It seems a little bit long-winded when we first see it. But basically, the way it works is each number that we have in this triangle is basically the sum of the 2 numbers above it. Each number is the sum of the 2 numbers above it. Now, some schools and colleges don't put a lot of emphasis on this because you can do a lot of this stuff without, knowing this too well, and you haven't got to quote it or anything, but it's handy to understand what this is. So each number is the sum of the 2 numbers above it. So for example, this 2, 1 plus 1, this 4, 3 plus 1, this 10 is like having your 6 plus your 4. So you generate the numbers below by adding the 2 numbers above it. And then we can see how it works. Okay, it's also symmetric And it's also fundamental for this thing called combinations that we're going to be doing today. Now, what's really cool is there's loads of patterns in there. So you have all the ones, you have the counting numbers, you have the triangle numbers. And if you carried this on infinitely, those patterns would continue. There's loads going on in here. There's books written about this where there's loads of little studies of different patterns you can find navigating your way through this triangle. For example, 11 to the power of 0, 11 to the power of 1, 11 squared, 11 cubed, if you write those numbers out. But what we're going to be using Pascal's triangle for is understanding this idea of combinations, how many ways we can group certain things. So I'm going to teach you some notation for this and show you how to speed this up on the calculator. But it's handy to know that. So just so you're aware of what Pascal's triangle is, that's it. And you might have seen it before. But what we're going to move on to is something called combinations. And we see this NCR. You'd read this as N choose R. And you might have noticed this button on your calculator as well. So N choose R is basically defined as the number of possible, and this will be a little bit wordy, this definition, but the number of possible combinations. And do feel free to ask if once I've written this definition, you're still a little bit confused. But I think when we see it with examples, it will make more sense. So the number of possible combinations of R amount of objects, from a selection of N distinct objects. So I will explain what this means because I appreciate this feels very wordy and pure mathsy kind of definition. And it happens to also be the value of the rth term in the nth row of Pascal's triangle. So what we'll do is we'll practice actually just finding this in the calculator and working out what it actually means in a context. Nth row of Pascal's triangle. And once we've given ourselves the time to understand what this is, it will make the topic a lot easier. So for example, what we're saying with that is Pascal's triangle, which we know goes 1, 1, 1, 1, 2, 1. It starts like that. That's like 0, choose 0, and then 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2. Now do check you can access this on your calculator. I think it's generally above the divide button if you press shift and it puts the little letter C there. And if you type 2, choose 0, it should spit out 1. And if you type 2, choose 2, it should spit out 2, and so on. And so you can generate all the Pascal's triangle numbers on any row if you use this combinations thing. So just check you can see where that button is. And we'll talk about how it works and what we're actually doing with it. Just a quick reminder as well of what a factorial is, because not everyone sees this at GCSE. N factorial, excellent, thanks. Yeah, you found it on there, superb. Good, so that's the button. So check that you can type in like 5, choose 1 or 2, choose 0 and see that it spits out a number. Very good. So what a factorial is it's basically all the numbers times together up to that number n. So for example, if I asked you 5 factorial, and that's 5 and then the exclamation mark, which again, you can access on your calculator, what the calculator is doing is it's doing 5 times 4 times 3 times 2 times 1. And this is very important. And I'll make that clear in a minute why we would want to do that. Another little rule is that 0 factorial comes out as 1. So what a factorial is actually doing is it's telling us how many ways we can arrange that number of things. So if I had 5 objects and I wanted to know how many different ways could I order them, it is actually 5 factorial. It's 5 times 4 times 3 times 2 times 1. So it tells you about the amount of arrangements of different items you can have. Who's seen that before? So if I basically had 10 horses running in a race, and I wanted to know how many different ways they could actually come in, how many different results there could physically be with all those 10 horses, it would be 10 times 9 times 8 times 7 times 6, or 10 factorial, all the way down to 1. So what this n choose r thing is doing is it's actually looking at how many combinations there are out of n amount of things if I restrict a certain amount of them. So n choose r. So basically what the calculator does is it does n factorial over r factorial times n minus r factorial. And we probably just need to see this with numbers, but that's basically what the formula is doing. Some things to just note as well is n choose 0 is actually 1 and n choose 1 is actually n. No worries, thanks Zach, that's okay. Excellent, lovely, thanks for that. Well, no worries, if anyone has any questions as we go through, obviously please do ask me, but the video will be there afterwards, so if you want to sort of pick up from here. But yeah, I'm just going to define a couple of quick things and do tell me if this is unclear or if you haven't seen this before. So n choose 1 is n, and it's actually the same as n choose n minus 1. So basically it's like saying on this row here, 2 choose 1 is 2. And likewise, n choose 0 is 1. Whatever row you're on, the first thing is a 1 and the last thing is a 1 as well. And we know that from Pascal's triangle. So I think we need to see some sort of number examples of this. But we're going to really look at how we can use the calculator to work this out and then start relating it to some actual problems. So if I just move on, if you guys that have access to the chat can just give me a little checkpoint on how you feel with that so far in terms of confidence. And be absolutely honest, because I know for some people this is very new. So I want to address it if it's like something you haven't seen before. But just a 1, 2 or a 3 with how you're feeling. And if you've got access to the calculator in front of you, it might be that you've just been trying out that choose button and checking you know where it is. But yeah, just give me an idea just to see sort of where you're at. If you want to put a 1, 2 or a 3 in the chat. And then what we're going to do is look at how this content will come up in an exam style question. Thanks, excellent. Well, feel free to put those in the chat as some of you are doing. That's great. Just to give me a little idea. Because what we're going to do now, if we're going to look at this example, no worries, so it might be quite new for some people here. So 40 choose 4 is what this is a way of denoting. This is 40 choose 4. Now you could actually type that into your calculator and see what comes out. But actually it doesn't even want you to work this out. It's just using the formula we mentioned here, which is what is 40 choose 4? Well, it means 40 factorial over 4 factorial, and then 40 minus 4 factorial. So basically the value of b is literally just 36. That's all it's looking for. So remember the formula for n choose r that we just mentioned is the thing on top factorial over r factorial n minus r factorial. So in this case, all that means is it would be 40 factorial over 4 factorial, and 40 minus 4 is 36 factorial. So b is just 36, and we can just know that from the formula. Okay, that is how the formula works. These numbers always add up to the n at the top. Okay, so if I said 40 choose 10, that would be 40 factorial over 10 factorial, 30 factorial. So this is just what the calculator would be working out. So for this one here, this is actually great because this one puts it in a bit of a context. At a dog show, 3 out of 11 dogs are selected for a national competition. Find the number of possible selections. So can anyone think what calculation we would do here? So it's 3 out of 11. And this we can see there's actually a practical use for this. 3 out of 11. So there's 11 in total. That's like n, the total number. And we want to specifically like pick 3 of them out of it. So how many ways are there of grouping 3 random likely selected dogs out of 11 different dogs? So the way you would do this is it would be 11 is n, and the amount we're restricting it to is 3. So it's 11 choose 3. So you could use that button, or likewise, you could do this calculation here. And what do we get? Let me do it myself. So 11 choose 3. Has anyone got an answer to that? So there are 11 dogs to pick from, and we want to see how many different combinations of 3 dogs we could make out of all of those groups. So there's loads of ways it can be arranged. So if we do 11 choose 3, we actually come out with the number 165 different ways of grouping 3 dogs out of a possible 11. Does that kind of make sense to everyone? Has everyone managed to get that number? So in the calculator, you might have typed 11 choose 3, or you might have actually typed this in. But either way, you should have got 165. Let me know if you got that, because that in itself is a skill. That is very much understanding combinatorics and understanding how these combinations work. So let me know if you managed to get to that number, 11 choose 3. Because what this is effectively saying is I've got 11 things and I'm restricting 3 of them to be specific dogs, and the other 8 are the other amount. So restricting 3 out of 11 is the same amount of ways of restricting the other 8, which is why 11 choose 8 is the same as 11 choose 3, because those Pascal's triangle have those symmetries from both ends. If you fix this many, like on a massive tree diagram of 10 branches that you can win or lose, if you have 7 wins, you in turn have 3 losses. So 7 out of 10 when it's binomial is the same as 3 out of 10 if you're restricting certain pathways. So that number comes out as 165. So what we're going to do now is actually relate this to expanding brackets. So yeah, do feel free to ask me any questions though, or clarify anything, because I know combinations is quite new as an idea. So we're going to look at binomial expansions now with brackets and see how this combination stuff filters in. So to start with, if we were to expand this first bracket here, does anyone know what anything to the power of 0 will equal? Because we don't typically do an expansion like that. We sort of have seen maybe this, and this before, but what is anything to the power of 0? Well done, excellent guys, superb. Thanks for the answers. Anything to the 0 is 1. Okay, brilliant. Now, if I have x plus 1 to the power of 1, that is just x plus 1. Or in other words, that is like 1x plus 1. Now here, if I have x plus 1 squared, that's a sneaky double bracket. That basically comes out as 1x squared plus 2 x's, because there's more of those middle terms to tidy up, plus 1. Now, I did it earlier, but if I do the same for x cubed, I get this, and some of you might spot the pattern that's emerging here, and we might be able to make the link with Pascal's triangle over here. And as a result, you might be able to guess what this expansion is, because this directly relates to Pascal's triangle. So let me know in the chat if you can see the link. Because we know as we increase the number of brackets, it gets more and more tedious, more and more involved, trying to tidy all those internal combinations up of, right, there's an x squared from those 2 brackets and an x squared from those 2 brackets and the first and last one and this one. So actually, we want to know how many little combinations we have. So what we would get for this is actually 1x to the 4 plus 4 lots of x cubed plus 6 lots of x squared plus 4 lots of x plus 1 on the end. Okay, and hopefully what we can see is these numbers in Pascal's triangle for this scenario just relate to the coefficients, but they sort of give us how many combinations of getting that term we have. And we've obviously done the example of 1 plus x, like it couldn't be a much simpler bracket than that. That is probably the ideal bracket to use this for. But what it's giving us is it's showing us that's the amount of ways of arranging how many x cubed terms can we get is coming from this many places. How many combinations of an x squared term are we going to get? So this is using Pascal's triangle, or this idea of combinations, to tell us how many ways there are of getting that term. So this is really kind of crucial to the background of what's going on. Now for this one then, in general, what this will mean is we have one lot of x to the n plus, and then what it will be is n lots, or actually I'll go the other way. If we go in ascending powers of x, there'll be 1 plus n lots of x plus n choose 2 lots of x squared plus n choose 3 lots of x cubed, all the way up to n choose n lots of x to the n, and n choose n is just 1 again. So you get all these symmetries from both ends of how many combinations of each coefficient you can have. Now, I do know this is a very new idea for a lot of you, so it's quite a lot to take in. And the notation is quite tricky as well, but do feel free to ask, because we're going to push on to some slightly trickier and more involved examples now. And I appreciate it might be quite quick that we're going through it. So do ask me to go back if you'd like, or slow down. Are there any questions? Does anyone have any questions in the chat? Do let me know if you're confident with this, or this you've seen it before. But also equally let me know if this is very new, because it kind of gives me a good idea as well. But yeah, well done. If you're following that and you're happy with it, superb. Because as I said, at year 12 and 13 is quite a new concept for a lot of people. So I've got an eye on the chat if you do want to share any comments or questions as we go. I'll do this one as an example then for expanding this. I'm actually going to change this to x plus 1 to the 7. Why not? Okay, so what we're going to do, if I do x plus 1 to the 7 or 1 plus x to the 7, same thing. Basically, the first term, hopefully we're happy that this is a massive 7 bracket expansion, where the first non-x term, the constant term, would just be a 1 times a 1 times a 1 from every one of those 7 brackets. And there would only be one way of doing that. So n choose 0, 7 choose 0 is 1. There's only one way of doing it. And we're just times in a load of 1s together. So the constant term coming out is definitely a 1. Now the next term, which would be, there would be 7 ways of getting, would be n choose 1, 7 choose 1, which is 7. So the next term would be 7x. The term after that would be 7 choose 2, x squared. The next term would be 7 choose 3, x cubed, and so on, all the way up to 7x to the 6 plus 1x to the 7. So what's happening each time here is if I multiply across 7 brackets and I do a 1 times a 1, then there's 5 other brackets left. They've all got to be 7s times together. Or a 1 times a 1 times a 1, then there's got to be 4 of the other thing, of the x's times together, sorry. So as the amount of 1s decreases, the amount of x's increases and vice versa. But what this number is giving me is the amount of combinations of grouping those amounts of things. Good question, absolutely really good question. Do we need to memorize the formula? I think depending on the exam board, I think you are sometimes given this formula in the formula booklet, depends on the board. I think it's really handy to know it because it kind of then shows you've done enough practice, because the questions can rely on you knowing, like being able to understand this formula. If it's just a straightforward binomial expansion, you've got your calculator, that's generally enough to be able to do it. But more of the problem solving difficult questions that they do will sometimes require you to have an understanding of the formula. So I think it's a good idea to learn it, but if you get access to it in your formula book, then that's a bit of a bonus. So it's a really good question. It will depend on the board though, so do check. And you should be able to check online for your exam board what their formula book looks like, so you know, and that can be helpful as well. No worries, brilliant question though, because for a lot of people that's quite a big thing, and you can go in more confidently knowing what you're expected to know. Good. So what I was going to say here is, like, if we do 7 choose 2, hopefully everyone's happy. That's the same as 7 choose 5, because it's 7 factorial over 2 factorial, 5 factorial, and your calculator will work that out. So you can type that in, or you can type 7C2 or 7C5. And what we should see is that that comes out as 21. So what that's telling us is that out of 7 different things, if I want to restrict 2 of them, or in turn restrict the other 5 of them, how many different ways of doing that are there? There's 21 different ways of selecting 2 and 5 in little groups out of 7. So that means that when I get to those terms in this expansion, there's 21 ways of arranging that out of these 7 brackets. So that's really handy to know. And equally, it would be good if we can work out 7 choose 3, which is actually the same as 7 choose 4. And if we do that on our calculator, we end up with 35. And then what that actually tells us, if we put this all together, we end up with the bracket expansion as follows: 1 plus 7x plus 21x squared plus 35x cubed plus 35x to the 4 1x to the 7. So those numbers effectively became the coefficients. They told us how many different ways of combining stuff we could have. And so I do want to just take it a little bit slower now in case it's getting quite difficult. But hopefully we can see that the combinations are allowing us to, rather than do this massive expansion and then tidy up loads of things loads of different times and work out how many ways am I getting all these different x squared terms or x cubed terms. This tells you how many ways you'll have of getting that, which is really, really handy. So we'll do another little bit of explanation, a little checkpoint, and then actually an exam question to see how we go. But do feel free to ask, and thank you to those that have commented and asked questions today. This is really handy. We are doing a big topic quite quickly here, so I appreciate this might be new to you, but do feel free to comment, do feel free to ask questions as we go. I'm going to kind of give another little extension of this idea now, if the brackets are a little bit harder than just 1 plus x. So again, we're doing this very generally, and then we're going to look at a specific example. So if it's something like ax plus something to the power of n, what we do here is the constant term will be b to the power of n, because it will just be the b from every bracket times together however many bracket amount of times. And there'll only be one way of getting that, because it's just the last term of everything times together. Like imagine on a tree diagram and you wanted lose, 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 lose. You just have that one set of ways of getting it, all that last tail times together. So this is what we've got. And then the next term would be n times b to the power of n minus 1 times ax. And then the next term would be n choose 2, b to the n minus 2 times ax to the power of 2. So what's happening is, as you reduce the power of b by 1, you increase the power of the other thing by 1. So basically they add up to n every time. So what we're saying is, if you've got like 10 brackets and you want the 3 amounts of them, you've got 7 amounts of the other thing times together. So that's what we've got to pay attention to, which is why these ones are slightly more involved. So for this example here, let's think about what's A, what's B, and what's N, and what's R as well. So first of all, what's A in this situation? This is actually quite a ridiculous bracket expansion. This is crazy, like to expand something to the 21. The numbers are going to actually be massive. And it's probably quite an unlikely one, maybe in an exam, because you get such a huge number. Very good. The value of A in this situation, if we're comparing it to this, is 2. Well done if you spotted that. So we're going to kind of just go with it for this example, and then actually the exam questions we do, hopefully it'll be a little bit nicer actually. So well done if you got that, absolutely right. A is equal to 2. Well done if you've written these out. So B is minus 3. Well done. And N is 21. Very good. B is minus 3. N is 21. Now, I'm actually going to push it a little bit further and ask for R. What is this asking for, this question? But very good. Well spotted if you've worked those out. You're mapping this idea. You're going comparing this to this and working out what the numbers are. So thank you for that. That was brilliant. And then R, no worries. No, that's good, but it's worth picking up on. Yeah, superb though. That's great. But R, this is the bit people struggle with. Like, what is R? And R is like the thing you're restricting. R is the thing we're honing in on and want to work out. We want the kind of x to the 9 term. So R is actually 9. Okay, so we want 9 of them. And as a result, are we happy that in turn, we want 12 of the other thing? So if I want 9 lots of the x times together, that means that the -3 is getting timesed in there 12 amount of times. Because if you're timesing across 21 brackets, and I want an x to the power of 9 term, there's going to be loads of ways of arranging this. But if I've got 21 different things times together, 9 of which are the 2x, then that means the other 12 are all the -3s. And there's going to be so many different ways of working this out. So what this term will be is we basically want 21 choose 9 times -3 to the power of 12 times 2x to the power of 9. Okay, so 2 to the power of 9 is 512. -3 to the power of 12 is this number. And then finally, 21 choose 9. This one is ridiculous. And we need to times that by that by that. And that would be the coefficient of x to the 9, which you can see looks ridiculous. Like you would never have thought it'd be that massive, that number, but it actually is, because there's so many ways of getting that term, and it's across 21 brackets that we're timesing. That's just for one way, let alone the fact we want this many ways of doing it. No worries, that's okay. So we're looking at binomial expansions today. We're going to go on to an exam question in a minute, which is actually, I think, a bit nicer than this question we're just doing. So no problem. But what we end up with, I'm good, thanks. Welcome as well. Happy New Year. I hope everyone here is doing well. We're dealing with a really massive topic, so don't worry if this is a little bit daunting or we're thinking this is very new. It's hopefully just kind of insightful onto what we've got as this part of the course. So I'm just going to quickly write out what this is. But it ends up being such a massive number that we can do it in standard form. I think it ends up as like 7.99777 times 10 to the 13. So it's huge. What we'll do is we'll actually look at, oh, good question. Why is it -3 to the power of 12? Good. Excellent question. So just with reference to what we did here, that was a really good point. What we're doing for that x to the 9 term, that's okay, no worries, guys. If you've got anything you want me to go back over, please do ask. We're going to do an exam question together in a minute, which will hopefully give us a sort of blank slate on this. But in answer to the question, why is it -3 to the 12? That is absolutely right. It's because 21 minus 9 is 12. So what we're saying, there's kind of 3 elements to any term we want of this expansion. There's the amount of arrangements, the amount of ways that we can get 9 things organized out of 21. And then what you're going to do is in that expansion, any one of those arrangements, what you've done is you've times 21 things together. And are we happy that if the brackets are 2x minus 3, 2x minus 3, 2x minus 3, we're either timesing 2x's or -3's in that order of stuff. So what we're saying is if we want x to the power of 9, that means we've done the 2x times a 2x times a 2x, 9 of them, meaning whatever's left has to be all the -3's times together. So if I've done 9 of the 2x's, how many brackets have I got left with the -3's in? That would be 21 minus 9, so 12. So there's 12 of the -3's being timesed in there. So basically what we've got when we expand this is we've got a 2x times a, brilliant, no worries, but that was an excellent question because this is where it gets really tough. The amount of combinations of all of these things of that bit, of all of these things of that bit, which individually are quite big numbers and are quite involved processes. So brilliant, and thank you for asking that, because hopefully that's clarified it for a few people. But we're going to look at an example together now. So give me a little update again, and then what we're going to do is we're going to go on to an exam style question that's, I think, hopefully a little bit nicer than the one we just did, because those numbers were crazy. So here we go. 1, 2, or 3 in the chat if you want to give me a little checkpoint how you're feeling. Otherwise, let's look at this question now. Cool, thanks guys. So it says, find the first 4 terms in ascending powers of x of the binomial expansion of 1 plus 8x to the power of 10, where a is a non-zero constant. Give each term in its simplest form. Right, here we go. No worries, thanks for the update of how you're finding this. This will hopefully be a nice one to work through. So what we've got here is if we have 1 plus ax, we don't know a, but we just know it's a number, to the power of 10. Hopefully, first off, we're happy. Yes, so we've looked at Pascal's triangle earlier, and that's where these combinations come from that we can do on the calculator. So you could use Pascal's triangle. I'm going to do it a kind of formulaic way, like we've been doing, but yes, very good. This does stem back to Pascal's triangle. So this is effectively a 10-bracket expansion, but we're not going to times out 10 brackets. We're going to try and do this quicker. Now, if I did the 1 from every bracket, 1 times 1 times 1 times 1, how many ways are there of doing that? There's only one way, the first from every bracket. So 10 choose 0 is 1. And you're going to do 1 to the power of 10, which is 1, times ax to the 0, because you're not doing any of them. So the first thing is definitely going to be a 1. 1 times 1 times 1. So this is called binomial expansion. This is part of combinatorics. So looking at combinations and ways of arranging stuff. This is a pure topic, but it actually comes up in statistics as well. So this will be in pure 1 and pure 2. We're focusing on the pure 1 stuff today. It does actually also come up into some of the statistics as well, because of like tree diagrams and ways of arranging. So there's something called the binomial distribution as well. But yeah, thank you for that question. So this is the binomial expansion that we're looking at. So that's the first term. Now the next term would be 10 choose 1 times 1 to the power of 9 times ax to the power of 1. So what we've effectively done here is 10 choose 0 times 1 to the power of 10 times ax to the 0. But I just think it's long-winded to think of it like that. That is just 1. The first thing coming out of this expansion is definitely a 1. 1 times 1 times 1, 10 of them. Okay. Now, the next thing we're going to do is 10 choose 1 times 1 to the 9 times that. And then the next thing would be 10 choose 2 times 1 to the 8 times ax to the 2. And then 10 choose 3, and you guys could start working this out. That's no problem. Times 1 to the power of 7 times ax to the 3. Oops, not the 6. And they are actually the first 4 terms, but we're just going to tidy them up. So the first one is 1. Can anyone tell me what 10 choose 1 is? What is 10 choose 1? So you can type it in your calculator, but you might know it from Pascal's triangle. What is n choose 1 or 10 choose 1? 10 choose 1 is actually just what number? Feel free to type it in on your calculator as well. 10 choose 1 is actually just 10. Well done. And times 1 to the 9, 10 times 1 is still 10, times ax to the 1. So you get 10 ax there. Good. Right, the next one. 10 choose 2. Again, you can type that in your calculator. 10 choose 2. So it's 10 factorial over 2 factorial times 8 factorial. 10 choose 2 comes out as 45, I believe. 45 times 1 times ax squared. So that will become 45 a squared x squared. Then the next one, 10 choose 3. If you type that in, that's 120 times 1 to the 7, still 120. A cubed x cubed So these are the first 4 terms of that binomial expansion. Okay, and that's typically actually what they'll ask in an exam. I don't think for a 10 bracket expansion, they'll necessarily ask you to write all 10 out, because you can assess the skill even in the first few terms. So that's quite common that they'll ask you for the first few. So where they've asked for the first 4, they've not asked for x to the 4, they've asked for the first 4. So that includes the constant term, the 1 at the start. So that's another way of saying up to the x cubed term. So hopefully that's good. Now, this is quite a good bit to go on with. You guys happy with that so far? Does that sort of make sense how we've got that? Because if you can do that, that's actually really good. That's a good skill. That's sort of the sort of start of all of this, being able to do that sort of thing. Work out how many combinations of that thing times that thing, and the powers add up to n. So as I'm getting less of the 1s, I'm getting more of the AXs. Yeah, oh, it's tedious. It is a bit of work, but it's hopefully something that's formulaic and we can kind of repeat. Now, question B is the more problem-solving one here. So let's look at this one. This says, in this expansion, the coefficient of x cubed is double the coefficient of x squared. Find the value of A. Well, the coefficient of x cubed, the coefficients we've got for x squared and x cubed are these numbers here. So we've got to interpret this the right way round. So what it said is that the coefficient of x cubed is double this. So what that actually means is that 120a cubed is 2 times that one. Does that make sense? Can we see how we can form this equation from that information there? The coefficient of x cubed, 120a cubed, is double 45a squared. So basically 120a cubed equals 90a squared. Now this is actually okay to solve this one. I would divide both sides by a squared. And then I'd divide both sides by 120. That actually simplifies really nicely to A and there's our answer. A is 3/4 or 0.75. That's it. So that was the kind of little problem solving follow-up. And obviously it meant that we had to have done, part A, we should have worked through properly, but forming the equation and solving that is something we can do with whatever answer we got previously. So hopefully that was okay and we sort of followed that, but that's a good exam question to look at. What we'll do now is we're going to try and just fit in one more slightly challenging expansion here if we can, see how we go with these next few questions. So here it says find the first 4 terms of this expansion. Now this one has fractions in it. So let's have a little look for part A. 1 plus x over 2 to the power of 10. Now again, same thing, 1 plus, and then there'll be 10 lots of the next thing, x over 2, plus 10 choose 2 lots of 1 to the power of 8 times x over 2 squared. Okay, and if we tidy this up, what we actually get, so it's very like the previous example, but it's nastier in a way because you've got fractions as well, but it's the same process. So that would be 10 lots of x over 2 plus, remember that number was 45, but you could find it on your calculator as well, squared over 2, that was 120, x cubed over 8. And if we tidy this up, we know it carries on, but they only asked again for the first 4 terms of the expansion. So we can see this is quite a common way they'll ask in the exam. They won't ask for the whole thing. They'll ask for the first few. And then that's it as well. And 120 divided by 8. And so we're going to get 15x cubed. And they're your first 4 terms of that expansion. So this is actually another common follow-up. I don't know, those of you that have maybe done binomial expansion have seen that we sometimes use it to find an estimate of something. Now, if I want this to be representing this, I basically just need to say, well, what would x need to be to make 1 plus x over 2 equal 1.005? And what that would mean is that if we let x for part B equal to 0.01, do you guys see that 1 plus 0.01 over 2 is 1.005? So what it's basically just doing is saying sub in 0.01 as x to this expansion. So if we do that, 1.005 to the 10 is approximately equal to 1. Has anyone seen this side of it before? Doing it for a random question? Sorry, doing it for an estimate. Those of you that have done this might have seen this. I'm happy to explain why this works as well. But let me know, because at the time I remember thinking, why would you want to do an estimate for 1.005 to the 10 if you could actually just work it out on your calculator? Some of us have seen it. So the question was, when the question said the first 4 terms bit, brilliant question again. So that's the thing I try to remind everyone. A lot of people do think this means up to the x to the power of 4 term, but they forget that this x to the power of 0 term is a term. Like the constant term, the 1, is actually really important. So that is included. That is still a term. So that was a really good question, and it's a common thing. If it says do the first 5 terms, people misinterpret that as up to the x to the power of 5, but it would actually be up to x to the power of 4. Very good. So well done if you've seen that we do this subbing in 0.01 idea. But basically, if you work that out, I think we get a number approximately equal to 1.05114. Now, what I just want to explain of why this works is if you're subbing in a really tiny number into this for x, and you're doing it to the power of 10, it's quite negligible what x is. So when you have like an x to the 4, x to the 5 term, it's such a tiny amount of decimal places. Basically, the most significant figures of the answer come from the first few terms, which is why they only need you to do the first 3 or 4, which will be quite a common thing they ask. So that is good, that works. And then you could actually work the real thing out as well. You could just do 1.005 to the 10 and see like what actually is the answer. And it probably will be something very close to this number here. So that was hopefully really good. Right, I'm going to try and ambitiously just do one more similar sort of thing. This question here. So the first bit is actually asking us to do the bulk of the question. 1 minus 2x to the 12 and find the first 3 terms of the expansion. So what this will be is this will be 1 plus 12 lots of minus 2x plus 12 choose 2 lots of minus 2x all squared. If we work that out, it would be 1 minus 24x plus 264x squared, and then the expansion would carry on. Okay, so that's me doing this first bit, working out the first 3 terms. Does that make sense how I've done that? So I've basically done 12 choose 0 times 1 to the 12 times minus 2x to the 0, and that all came out as 1. Then I did 12 choose 1 times that to the 1 times the other thing, 1 to the 11, which is still just 1. That came out as minus 24. and so on. So they're the first three terms. Okay, so then final thing we're going to do, when it asks us to find x squared in this expansion, can I just check with everyone that's here that we're happy that this is now, so this is very common sort of follow-up question. This is a 13 bracket expansion. Does everyone see that? There's 12 of them and this random 1 plus 3x. Are we happy that that's a 13 bracket expansion? Obviously, we don't want to times out 13 things. And we kind of already know a lot about this stuff. So can we see that this part 2 question is asking us about effectively 13 brackets, 12 of which are the same, and we've sort of dealt with in part 1 of the question. Does that make sense to everyone? So part 2, we've gone from a 12 bracket expansion to a 13 bracket expansion, where 12 of them are the same, but one of them is different. One of them is a different bracket. Yeah? This is a common follow-up, and you'll see it in the textbooks as well. But this is now using your first part answer to help you with the second part. So we know now that what this is that it's 1 plus 3x times a 12 bracket expansion, that actually, if you did that expansion, it would start off like this. Then there'll be a something x cubed, a something x to the 4, all the way up to the 12. But we actually don't really care about all the other terms, because I only want to know for this 13 bracket expansion what's going on with the x squared bit when we times it all out. So this is the bit people rush, but I just want to check we're happy up to there, that we've kind of dealt with this part. Because of part I, we know the expansion of those 12 brackets starts off like this. So ultimately, across 13 brackets, if I want to know what the x squared term is doing, well, I'm going to times everything by 1 in here and everything by 3x to expand that final bracket with everything. So the x squared term is going to come from the 3x being multiplied by the minus 24x, and also it's going to come from the 1 being multiplied by the 264x squareds. So ultimately for this 13 bracket expansion, we're going to get minus 24 times x times 3x and 1 times 264x squared. And so what we'll get is we tidy those up and we end up with 192x squared. Okay, so hopefully that's clear, but that's a really good extension question to look at. So there are a few of them in the textbooks, and this, again, this is a really good example of an exam question that they could ask. So yeah, so I think we've dealt with quite a big topic there today, starting from Pascal's triangle, which we did way back at the start, and looked at how it filtered in to combinations and the sort of choose aspect of this. I think we've got quite far with this topic. Now, this is something that's, as I said, very new to a lot of people, quite involved, and something that, you know, you might need to dedicate a bit of time to practicing, but once you've got it, it is actually very formulaic in the exams. So it's just one of those new topics you've got to commit a bit of time to practicing. But yeah, very well done. And thank you so much to all the answers and the questions as we went through that. There were some brilliant comments in there. So really, really well done for taking that time on a Sunday to work through binomial expansion. If you've got any quick questions for me, do feel free to ask. But otherwise, thank you very much for joining. It'd be great to see you at a session sometime soon. Also, check out the Snap Revise platform, because there's loads on there really tailored towards revision for all the different boards. Well done. Thanks, guys. Keep well. And hopefully see you at a Sunday YouTube session as well soon. But as I said, do check out the Snap Revise resources and content on the website, because there's lots really geared up exactly for your different exam boards and so on. So hopefully be really useful for you. But really well done. I'm going to stop sharing that there and just say thank you again. And yeah, have a really good week and hopefully see you at a YouTube session soon. Thanks, guys. Well done. Bye. Well done. Thanks.